Okay, hi everyone. We're going to get now into section 6.3, which is function operations and composition. Okay, so what we're looking at here is how to combine functions now in various different ways. I'm going to put some lines in here. We're going to start off with some basic ones: addition, subtraction, multiplication, and division. So now we're looking at functions as the objects themselves. So for instance, we can say, instead of saying let's add a number to a number, let's add a function to another function. So the first example is I've got function f of x is 5x, function g of x is x plus 2, and I'm going to add these two together. Okay, so h of x is the sum of f of x plus g of x, and that just simply means I'm going to take h of x will be 5x, which is f of x, plus x plus 2, which is g of x. Now I always try to use parentheses even when it doesn't need it. Well, this is going to be 5x plus x plus 2 is 6x plus 2. Let's look at subtraction. So subtraction, if h of x is defined as the difference between f of x and g of x, I'm going to have 5x, and this is where the parentheses become important, x plus 2. So now I have 5x minus x minus 2, so I have 4x minus 2. Multiplication, again, parentheses here are going to be important. So I want h of x is going to be the product of f of x, which is 5x, and g of x, which is x plus 2. Now I distribute the 5x through and I get 5x squared plus 10x. And division. Now division is an important one. I have to make a little bit of a stipulation here. 5x divided by x plus 2. And notice, x cannot be negative 2, because if it were, we would divide by 0. So when we have the division, we need to put in a little stipulation that for all values of g of x, all values of x, where g of x is not 0. So that has to be a stipulation we make, right? Because x plus 2, I can plug any number into g of x, but if I plug it into the denominator of h of x, I get an undefined value. Okay, so let's just do a quick review of domain and range. We're going to spend most of our time with domain here, but I want to define range at the same time. So domain and range, when we're talking about a function, the domain is all numbers that we can plug into a function, and the range is all numbers that can come out of a function. So a good example of that is previously here, where we looked at this function here. The domain of g of x, I can plug any number into this, but then the domain of h of x, I cannot plug in negative 2. Okay? So let's look at these functions here and see how it relates. So, 6x, what numbers can be plugged into 6x? All real numbers. And remember that? That's a symbol for real numbers. It's like an R with an extra line in it. All real numbers. So basically that just precludes no complex numbers. This one's a little different. Remember, this is something we were just talking about, x to the third to the 1/4. Now remember that anything to the 1/4 power, so if I write this as x cubed to the 1/4 power, well, I can cube any number, that's okay, but I can only take an even root of a positive number. So this is all reals such that x is positive. Okay, so that's our domain here. Now let's take a look at f of x plus g of x. That's going to be 6x plus x to the 3/4. Now, let's see what we can plug in here. I can plug positive numbers in here, no problem. But if I try to plug a negative number in, it's okay here, but here we have a problem. So the domain of this function is going to be the same as the domain of g. All real numbers such that x is positive. Okay, and in this case, we really don't need to write the reals there. We're going to assume that it's real numbers. Okay, same here. Let's take a look at the product. This might be a little interesting. Okay, I get 6x times x to the 3/4. Well, now what happens when I multiply two things? Well, I have x to the first times x to the 3/4. Well, then I add the exponents. This becomes 6 times x to the 1 plus 3/4. This is 4/4. So I get 6x to the 7 over 4. Okay, now I can take anything to the 7th power. That's okay. But again, the problem here is I cannot take the 4th root, because that's what 1 over 4 is, or 7 over 4. I cannot take the 4th root of a negative number, so this is again all positive numbers. Finally, the division one is a little tricky as well, because we're going to see the exponent changes here as well. Okay, so I'm going to get 6x over x to the 3 over 4. Now again, here remember we subtract. So I get 6x times x to the negative 3/4. So this is going to be simplified x to the 1/4. Right? Because I have x to the first minus x to the 3 over 4, and I'm left with x. So again, this ends up being all positive numbers because I can plug in anything into this except I can't plug in negative numbers. Okay? So typically with these problems, when we talk of domain, we're usually speaking of the domain as a subset of the real numbers. Okay, so now let's look at composition. So the composition is the idea of putting one function inside of the other. That's how I want you to think of it, putting one inside of the other. So we write it this way: h of x equals g of f of x. Now, I'm going to introduce a slightly new notation here that the book is not using, at least in this chapter, and that is we can also write h of x as g with a little open circle, like that, of f of x. So it's like kind of like the multiplication dot, except that it's open. Okay, so this means the same thing here. I think this notation is useful for some applications. For us, though, this notation is going to be probably more useful. All right, so that's what it means. You put one inside the other. Now, one thing we have to talk about here is the domain again of h of x, because now we had a domain of g, we had a domain of f, and now we put one inside the other. That might change the domain. Okay, so the domain is all numbers, all the input values, all the numbers in here, such that x is in the domain of the inside function and in the domain, and f of x, when I throw it through f, it's also in the domain of g. So here's a picture. I like this picture a lot. The book has this picture. I just animated it a little bit. So if we have a value of x in the domain of f, okay, it goes into the range of f. Likewise here, if I have a value in the domain of g, it goes into the range of g. Okay, domain to range, domain to range. And so what I'm going to do here is what happens now if I put f inside of g. Okay, that means that I put a number into f, it goes into, I put a number for x into f, it goes to the output of f, and then g picks that up and puts it into the output of g. So it goes this, the chain is from left to right along this diagram. X to f of x, and then we would put f of x to, and then it's still blue here, so f of, g of f of x. That's the chain. X goes from here to here, and then g picks that up and goes from here to here. And again, it's blue, so you can't read that. Okay? So here's what I'm going to do. I want to give you a sense of what this domain looks like. Okay. So these are all the values in f that can go into f, and these are all the values that can come out of f. These are all the values that can go into g, and these are all the values that can come out of g. So what's happening here is as these two, one goes inside each other, it's possible that the range of f is the same as the domain of g. That's possible, or very, very close to it. In which case, if it goes into f, it comes out of f, goes straight into g, and out of g, and there's no problem. But sometimes they're not the same. Let's look at that. Sometimes they're a little bit different. Sometimes one is smaller than the other, or they don't overlap quite the right way. So this is a situation where suppose x was here, okay, and suppose f of x went into the range of f, but look, it's a number that's in the range of f, but not in the domain of g, okay? So even though this is in the domain of f, it's not in the domain of g of f of x. It's in the domain of this, but it's not in the domain of this because when I put it through f, I can't then put it through g. Okay? So that's an important thing to think about. Now likewise, there's also something else funny that can happen. We could have something that was in the domain of g, right? Like we just said. We could have something that was in the domain of g, okay? But there's no way for f to get to it, right? It's possible, pardon me, I've driven in the wrong spot. Here's a number that's in the domain of g. G is kind of the greenish one. It's in the domain of g. That is, I can put it into g. It's cool to put it in here, and I'm going to get a valid output. However, there's no way that f can map to it. Okay, there's no way that g, so that if I put in a value for f, there's no way that this number can end up inside of g. Okay, so this is a situation, I just want to show you a picture. This is kind of a graphical representation of what can happen when you have two functions and you're putting them together inside each other. They could be the same, they could be different. Okay, in order to chain through, we have to go from here to the whatever the overlap is to the output. Okay, so let's look at some examples of how this might work in practice. So I've got, first of all, let's just look at a basic situation and get comfortable with the idea of what it means to put one function inside of another function. Alright, so here I'm going to say this is f of x, 2x minus 7, and g of x is x squared plus 4. I'm going to put 3 into f, and then that's going to go into g. So here's what it looks like. I'm going to put 3 into f. So 3 goes into f. F of 3 equals 2 times 3 minus 7. That's 6 minus 7. That's negative 1. So f of 3 is negative 1. So g of f of 3 is the same as g of negative 1. Now, I put negative 1 into g. Negative 1 squared is 1, plus 4 is 5. So, g of f of 3 is 5. All right, let's look at a couple examples here where we're looking at domain and range. So I have two functions. This is interesting, and I can rewrite this if we want. 4 over x, and this is g of x, x minus 5 of x minus 2. Let's see what happens when I put g inside of f. Well, here's g. I'm going to put it inside of f. So I'm going to put this function into the input of this function. Now the input of this function is x. So I'm going to put 5x minus 2 in place of x here. So I end up with 4, and in place of my input here, I put the entire function g. Okay. Now let's look at what happens if I put f inside of g. Well, g is 5x minus 2. So I take the input of g, I multiply it by 5, and I subtract 2. Well, now my input is f. So I go 5 times 4 over x minus 2. I put the entire function g inside, the entire function f inside of g. Finally, now this is kind of an interesting one. This is f of x. I'm putting f inside of itself. Well, this is f, 4 over x. Okay? So, inside of f here, I'm going to put another copy of f inside. Oh, that shouldn't be a 3 on the denominator. That should be a x in the denominator there. Okay. All right. So let's take a look at the domains here, which is pretty interesting. Okay. So remember the definition of domain here is that it has to be in the domain of g to start with. Okay. And then all the outputs that come out of this have to be in the domain of f. Let's see. The domain of g is all real numbers, so that's okay. Okay. Now, when I put that output into f, I better have an output that works. So let's see. I cannot, if I look at this particular function, I can't have an output where the denominator is 0. So that means my domain is all numbers, so that does not happen. The only time that happens is when x is 2/5. So the domain is all numbers except 2/5, right? Now remember, the domain of f was x can't be 0, and the domain of g was all real numbers, and now the domain of the combined function is all real numbers except for 2/5. Let's look at this function here. Okay, I'm putting f inside of g. Now, that means that I have to have, the numbers must be in the domain of f, and any outputs that come out of f better be in the domain of g. So let's see what can go into f. F is 4 over x. Anything but 0 can go in there, so I'm going to say automatically 0 cannot be in my domain. Now, the numbers that can come out of here are real numbers except for, well, 0. But notice that anything can go into g, that's okay. So anything that could possibly come out of f can go into g. And since anything that can go into f is all numbers except for 0, our domain is all numbers except for 0. And we can look at this and see that's true. This is 20 over x minus 2. The only number I'm not allowed to put into f, pardon me, the only number I'm not allowed to put into this function is 0. This one's a little funny. Okay. Now here what I'm going to do is invert and multiply, and this ends up being x. All right, now we have to be careful about this. This is a very strange situation. What I have here is I have the function where f of x is put into f of x. We have to go back. What numbers can go in here? You say all real numbers. Well, not quite. Okay, this is a very strange situation we're looking at here. This is true that if I had the function y equals x, I can put any number in for x. But here I'm in a very interesting situation. We have to look at the definition of composite functions. Let's go back and look at it. The domain of your composite function is all numbers such that x is in the domain of the inside function, okay, and whatever my output is in the domain of the outside function. Well, the domain of the inside function is all real numbers except for 0. Okay. Now, the domain of the outside function is, again, as long as this is never 0, we're okay. And this is never 0, okay, because the domain of the range of this function is all real numbers except 0. So even though the function just looks like our standard old y equals x line, it's actually the y equals x line without a 0. Okay, so this is a very fascinating idea of how we have to look at these functions. All right, so we're gonna break this down more in class and do a lot of practice in the next couple days. Thanks for watching.